Welcome back to the workshop. Module 6 is an overview of the flexible and semi-rigid pavement design strategies. We just finished explaining the fatigue cracking models and transfer functions of flexible pavements. This session, or Module 6-1-4, will focus on the regression equation used to predict increases in IRI, or the smoothness degradation of flexible pavements. For flexible pavement smoothness degradation, the same type of information will be discussed as was included for jointed plain concrete pavements and continuously reinforced concrete pavement smoothness degradation within Module 5. Thus, the same information will be presented, but in a more brief form because the measurement equipment, IRI definition, and design premise are the same for all pavement design strategies. There are 3 learning outcomes from Module 6-1-4 on IRI, or flexible pavement smoothness degradation. These learning outcomes include explaining and defining the design premise for smoothness degradation of flexible pavements, defining the increase in IRI predicted for flexible pavements in the Pavement ME design software, and describing the regression equation for predicting increases in IRI over time and throughout the design period. Starting with the definition and measurement of flexible pavement smoothness, or IRI. This information is the same as was presented for jointed plain concrete pavements and continuously reinforced concrete pavements in Module 5. Basically, smoothness is defined as the variation of surface elevation within the wheel paths that induce vibration in vehicles. Smoothness is quantified by the International Roughness Index, or IRI. IRI is basically the sum of cumulative movement in one direction between an axle and body of a standardized vehicle. IRI is a mathematical index of the longitudinal profile of a road expressed in meters per kilometer or inches per mile. IRI has been adopted as the standard measure of smoothness by the Federal Highway Administration and many individual state highway agencies. IRI is used to quantify smoothness in the Pavement ME design software. Smoothness in the Pavement ME design software is used to predict pavement functional performance of a flexible pavement from a highway user's perspective. Smoothness is measured using the same equipment and methods discussed for jointed plain concrete pavements and continuously reinforced concrete pavements in Module 5. IRI is measured in accordance with AASHTO R43M and R43-07, or in ASTM E1916. The IRI is computed using profile measurements from devices such as the inertial profiler, the dipstick, and a rod and level survey. The devices commonly used to measure smoothness are the high-speed inertial profilers and the lightweight low-speed inertial profilers. The next session is to overview the distress mechanism or design premise used to determine the deterioration or degradation of smoothness after initial construction. Smoothness degradation, or the increase in variability in the pavement profile point by point in the wheel path over time is not predicted using mechanistic empirical concepts in the Pavement ME design software. The approach used or applied in the software or in the MEPDG was to develop a statistical model or regression equation to determine the change in IRI from field data, which includes key factors such as the initial IRI, the increase or change in structural distress, and a site factor to account for subgrade differential movements, climate fluctuations, aging of the asphalt wearing surface, and other surface degradation. The design premise for predicting increases in IRI from the time of construction is the same as for jointed plain concrete pavements and continuously reinforced concrete pavements. The only difference is that different distresses are used and the site variables are different. The smoothness generalized model or regression equation is displayed on this slide. The IRI predicted over time is based on the initial IRI measured after construction, the structural distresses predicted over time, multiple structural distresses predicted over time, the site factor that is related to the subgrade site properties and climate, and then the regression coefficients or constants of the dependent variables for the site factor as well as each of the individual structural distresses. Next, we will present and discuss the regression equation for calculating IRI throughout the design period based on that design premise for a flexible pavement design strategy. The flexible pavement smoothness degradation regression equation is basically included or shown on this slide. The IRI is calculated using the average total rut depth, the average total area of fatigue cracking, the average length of transverse cracks, and the site factor. The calibration coefficients of the regression equations are also listed on the slide. The calibration coefficients for each individual distress are C1, C2, C3, and C4. Basically, C1, the rut depth coefficient is 40. The C2, or the fatigue cracking coefficient, is 0.4. C3, or the transverse cracking coefficient, is 0.008. And C4, the site factor coefficient, is 0.015. The values for the calibration coefficients may vary between different publications of the MEPDG Manual of Practice, depending on the results of any recent global calibration. The coefficients of the transfer function are also included in the output report for the Pavement ME design software. The site factor variable of the smoothness regression equation is included on this slide. The independent variables of the site factor include age, the freezing index, the percent passing the 0.02 millimeter sieve, the average annual precipitation, the plasticity index of the subgrade soil, and the percent passing the number 200 sieve or the 0.075 millimeter sieve. This slide summarizes the coefficients that were derived from the global calibration of the regression equation for predicting the IRI throughout the design period. The calibration coefficients include the C1 of 40, which is the rut depth coefficient, C2 of 0.4, the fatigue cracking coefficient, C3, 0.008, or the transverse cracking coefficient, and C4 of 0.015 for the site factor coefficient. The graph included on this slide shows the use of the preventive maintenance and its impact on IRI after it's been applied to the flexible pavement. Simply just shows at the time that the preventive maintenance strategy was applied, there is a reduction in IRI, resetting the vertical profile of the asphalt surface. And then the Pavement ME software simply continues to predict the mean IRI, and then the IRI at some reliability level over time, using the structural distresses that are present or calculated on the pavement surface. Reliability was discussed in detail in Module 3 and how it is applied in the Pavement ME design software. The standard deviation of the residuals for the flexible pavement smoothness is displayed on the slide. The standard deviation of the residuals is used to determine the reliability as related to smoothness of flexible pavements. This section is a summary of the materials presented under Module 614 that were just covered for flexible pavement smoothness degradation. There were 3 learning outcomes from Module 614 on flexible pavement smoothness. These 3 learning outcomes included: we explained the design premise for smoothness degradation of flexible pavements. We defined the increase in IRI predicted for flexible pavements in the Pavement ME design software. And we described the regression equation as well as the standard deviation of the residuals for increasing IRI over time. This ends Module 6-1-4 on flexible pavement smoothness degradation. The next submodule of the training course, sequencing, is Module 6-1-5 on the interpretation and adjusting design features and factors to achieve an acceptable flexible pavement design.